think we should start. Great pleasure to introduce our colloquium speaker for today, Professor Junichiro from Rice University. Jun got his most of his education in the University of Tokyo, undergraduate, and then he was a PhD student at SUNY Buffalo, and then postdoc in Santa Barbara, and then Hansen Research Fellow at Stanford, before he became a professor at Rice, where he's now a professor of 3 departments: physics, electrical engineering, and material science. And he's got many awards and accolades. He's a leading expert in the area of many-body collective interactions, including various nanostructures, semiconductor, carbon-based nanostructures, the whole array or the whole spectrum coverage from sub-terahertz to optical visible wavelengths. His lab footprint is probably larger in Rice than the combined labs of all the physics departments. I would guess it has amazing facilities from magnetic field, terahertz, low temperatures, high temperatures, everything possible. And among other things, he is the founder of an award-winning program which is called Nano Japan, which sends undergraduate students of summer research in Japan. And many of our students at ANM, well, at least some of them, benefited from this program. Great. Actually, some of them are still here as graduate students. Anyway, without further ado, let's welcome Jun.
Thank you very much for a nice introduction. So it's a great pleasure to be here today. Can you hear? Is it working? Good. Okay. So yeah, good afternoon, everyone. So I'm honored to be part of the Lee Fest, and today I will talk about Diki phenomena. So Robert Diki was one of the most well-respected physicists in the last century, and so he was extremely productive. And it's almost impossible to find a physics discipline where he did not do any important work. So he's best known for the development of the lock-in amplifier during the war. Also, he developed a very sensitive microwave detector called the Diki radiometer. But then after the war, he switched to AMO. He became a theorist, quantum optics, and so whatever he did, so he discovered something, and it has his name: Diki narrowing and Diki superradiance. And then after that, he went to gravity, cosmology, and so on. So there are many types of Diki phenomena, but today I will talk about Diki superradiance, which has a wide range of applications to not only at AMO but also condensed matter, especially nowadays. So let me begin with a simple explanation of what he considered back in 1954. So he considered a collection of 2-level atoms, so N. There are N atoms, but they're all excited in the excited state. And if you consider the time evolution after this, if you don't take into account any interactions among the atoms, you obviously see spontaneous emission. So spontaneous emission is occurring independently. We have N different atoms and emitting randomly, and if you collect all the light, the maximum you can get is proportional to the number of atoms in this system, and so the decay time is independent of the number of atoms. It's just given by the radiative recombination time. But if you put them so that place all the atoms together in a very small region of space, very small volume of space, smaller than the wavelength corresponding to the emitted light, then the atoms automatically talk to each other, And you can easily see what happens if you just consider two. If you have two atoms and one goes down, that emitted light immediately interacts with the next atom. That will produce stimulated emission, right? So, but that's only between the two. But if you have many atoms, then coherence, macroscopic coherence appears, and then emission occurs at the same time. So synchronization occurs among all the dipoles, and emission occurs. Emission's intensity is now n squared, proportional to n squared, signaling that this is coherent. So that's why this is called coherence in spontaneous radiation. And the emission rate, the radiative emission rate is accelerated, proportional to the number n. So this kind of cooperative, so this is called cooperative radiation acceleration. Okay, so he coined this process of superradiance. And superradiance appears in many different branches of physics. All these are very recent papers, and so it appears in BEC and quantum dots and nanoplasmonic systems and nanolasers and semiconductor quantum wells. So whenever you have a collection of atoms or dipoles or oscillations, and they talk to each other through interaction with a common electromagnetic field. Okay, so this is a very universal phenomenon. For example, several years ago, in collaboration with Alexei, we demonstrated that this also happens in the cyclotron resonance of a two-dimensional electron gas in the quantum Hall regime. So we start with a two-dimensional electron gas and apply perpendicular magnetic field, and then the electrons move in the cyclotron motion. So we have many electrons, 10 to the 11th the electrons per squared centimeter, but these individual electrons are moving in synchronously. And we found that indeed the decay rate, we're doing time domain terahertz spectroscopy, and so the oscillations are due to the cyclotron motion. So we monitor this decay rate, and Alexei derived this expression. So there's no fitting parameter, and this works extremely well for explaining the data. A little more exotic type of superradiance is called superfluorescence. So this is, from a condensed matter point of view, this is more interesting because basically this is a three-step process. So you create an ensemble of incoherent dipoles. So initially, there's no correlation, no macroscopic coherence. But through this self-organization process, through the photon exchange process, macroscopic coherence appears spontaneously, right? And so there's a certain delay time between the creation time moment and the moment when the system emits light. So in this case, so the third process is the superradiance process. So that it decays suddenly with an accelerated decay rate, and so that this phenomenon has been observed in atomic systems, but we did the first observation of superfluorescence in a solid state system.
What was the final state in the previous of this
So the final state is vacuum, so nothing. Yes, yeah, right. So in the case of atoms, they all go down to the lower state. In the case of semiconductors, all the electrons will go down to the valence band. So this was done in a semiconductor, again in a quantizing magnetic field. So we create electron hole pairs here, and then after 100 picoseconds, all of a sudden these pulses appear. And these different peaks correspond to different Landau levels. Okay? But this was also explained by Alexei, and so the condition to observe the superfluorescence is that the so-called cooperative frequency. So this is the frequency, or this is the rate at which macroscopic coherence grows. So this growth rate has to be faster, larger than any decay processes. So in the case of solids, the most important decay is electron-electron interaction, electron-phonon interaction. So there are lots of fast decay processes, but this quantity has to be larger than any the phase breaking processes. So here D is the dipole moment, and N is the number of atoms or electron hole pairs. Delta is the degree of population inversion. Basically, all these can be enhanced by applying a magnetic field, and then the scattering phase space available for scattering will be significantly restricted by the magnetic field, so T2 becomes longer. That's why it was possible to observe superfluorescence. But one thing to notice here is that the square root of n dependence. So this will appear throughout the talk today. So this square root of n, the cooperative enhancement of light matter coupling. So G0. So this represents light matter coupling on the single atom level, but you have many atoms. So all these previous studies were done in free space. So from here, I want to switch gears and talk about our most recent experiments done in the cavity QED setting. So as you know, cavity QED is a very well-established field of research in atoms and molecules, AMO, quantum optics. But for condensed matter system, this is really a new hot topic. And again, I want to emphasize that this N, because condensed matter systems have huge numbers of atoms and electrons. So cooperative enhancement happens more easily in solid-state systems. So let me define some of the important features, the quantities in cavity QED. So G represents light matter coupling rate, and the gamma represents matter decay rate. So in our case, in solid-state systems, gamma is always given by phase-destroying scattering processes. And in addition, we have this parameter kappa, which is due to the finite Q value of the cavity. So there are three quantities, and we can define this quantity, the so-called cooperativity. And this compares the ratio between light matter coupling and the decay processes. And when C is larger than 1 or much larger than 1, light matter coupling is the fastest process, the most important process. So we can forget about decay processes. So this is the so-called strong coupling regime. So let me show you our data. So these are transmission spectra in a certain. I'll talk about more details about the experiment. I just want to introduce some of the quantities. These are experimental data. This is the so-called upper polariton. This is the lower polariton. Okay, so this polariton appeared due to hybridization of light and matter. So the light originally had this frequency, and matter originally had this frequency. They were supposed to meet here, but due to strong coupling, actually ultra-strong coupling, there's a huge splitting. So this splitting is called vacuum Rubby splitting. And the most important vacuum Rubby splitting is the on resonance vacuum Rubby splitting, which is equal to 2G. So in our case, the difference between this peak and this peak is 2G. And this should be compared to the line width. This is very, very narrow. So this is unusually narrow for a solid-state system. So this looks like an atomic spectra, but this was done in a solid in the terahertz frequency range. And so the line width basically gives us the decay rates, the average of the cavity, photon decay and the matter decay. So in our case, this parameter, the cooperativity parameter, is 4G squared over a gamma kappa is over 3,000 for this is for a solid state system. This is really a record high value. And this is due to the fact that we have many electrons, many body enhancement. Another important parameter is the ratio between the vacuum Rubby splitting and the resonance frequency. So this is essentially 1. So this is the unusual regime I want to talk about today. So the so-called ultra-strong light matter coupling. Yes? Yes, it's included. Yes, correct. And right. So yeah. So light and matter they couple to show anti-crossing. And so 2G is the vacuum Rubby splitting. G is the coupling rate, and omega 0 is the resonance frequency. So typically, when G becomes a significant fraction of omega 0, people say ultra-strong coupling. And if G actually exceeds omega 0, you can say you are in the deep, strong coupling regime. Whatever. So these are the words that the people use in the literature. All right. So I'll be talking about 3 experimental platforms. So platform number 1, Landau quantized. Right. So omega 0. So this is the frequency axis. Omega 0 is the yes. Okay. And so the first system is a 2-dimensional electron gas in a high Q terahertz cavity in a magnetic field. So here we study ultra-strong light matter coupling without light. So I want to emphasize that everything's happening inside the cavity. So the light or electromagnetic field we're talking about here is the vacuum fluctuation field inside the cavity. And the second system is a certain magnetic system, magnetically ordered system. So here we're doing cavity QED without light. So here we're talking about matter-matter interaction, matter-matter ultra-strong coupling. So the role usually played by photons is played by magnons in this unusual situation. The third system, if I have enough time, I'll talk about exciton polaritons in aligned carbon nanotubes. So here we found that because of the one-dimensionality of the carbon nanotubes, we can tune the ultra-strong the coupling strength just by changing the polarization. Okay, so let me start with the first system. So as I said, we're dealing with Landau levels. This is not graphene, so this is gallium arsenide. So it's a parabolic band. So in a magnetic field, we have equally spaced Landau levels. So the transition we're looking at is is from the highest occupied Landau level to the lowest unoccupied Landau level. So this is just the quantum mechanical picture of cyclotron resonance. And the omega c is the cyclotron frequency, which is proportional to B and inversely proportional to the effective mass. We are using one-dimensional terahertz photonic crystal cavities. The idea is to alternate silicon, vacuum, silicon, vacuum, silicon to make a Bragg mirror on each side. And there's a huge contrast. Index contrast. The index of silicon is 3.42, whereas the index of vacuum is 1. So because of this large index contrast, we don't need to repeat many layers. If I have just 2 layers of silicon, the reflectivity in this range is already 97%. And if I have 3 layers, the reflectivity is already 99.7%. So for most of our experiments, we're just using two layers of silicon or 3 layers of silicon. And then this is a transmission spectrum through an empty cavity. So no material inserted. So you can see that the line width is typically 2.5 gigahertz, but so the center frequency is a few terahertz. So the Q factor is on the order of 1,000. and so corresponding to a photon lifetime of 70 picoseconds or finesse of 100. So for those of you who are not familiar with terahertz, so 1 terahertz corresponds to 4.1 millieV in photon energy, or 300 microns in wavelength, or 33 wave numbers. So what we do is we place a sample in the middle. This is a very nice laboratory, and we can put any type of condensed matter system, solid state materials here. And if we put gallium arsenide here, and then we can apply a magnetic field, and we do transmission measurements, and if the magnetic field is 2 Tesla, for example, the cyclotron energy is about 1 terahertz. Okay, so we are back to this figure. So there's something I didn't explain before. So first of all, this is the cyclotron frequency, omega c, which is increasing with increasing magnetic field. And this is the photonic mode frequency of the cavity. So they are supposed to meet here, but they don't cross. They show anti-crossing, like this, avoided crossing. So we're using circularly polarized radiation. That's why the direction of the magnetic field is important. So the upper part, we have the positive magnetic field, +1, +2, +3 Tesla. The lower part corresponds to -1, -2, -3. The reason why the direction of the magnetic field matters is the electrons are charged negatively, and in the presence of a magnetic field, they're moving only in one direction. And we're using circularly polarized radiation to probe this phenomenon. So therefore, this side is called cyclotron resonance active, meaning that the direction of the electrons and the direction of the circular polarization are the same, right? So co-rotating. But the bottom here, cyclotron resonance inactive. So the electrons and photons are moving in the opposite direction. So from this sense, they shouldn't interact, right? So classically, there should be no interaction. But we are seeing this, right? So if there is no interaction, the photon frequency should be here. But there's a visible, very obvious shift due to the interaction between light and matter, even though they are moving in the opposite direction. So this is direct evidence for the breakdown of the rotating wave approximation. So let me explain what that means. So that the simplest Hamiltonian what one can write down in this situation is the James Cummings Hamiltonian, which has 3 terms. This is the 2-level matter, and this is the quantized light, and the interaction between the two. And the interaction Hamiltonian has only 2 terms corresponding to absorption and emission. So you are destroying 1 photon and exciting the matter, and then you are creating 1 photon and going down, right? So there's also an extended version called the Tavis Cummings Hamiltonian. So the extension, so it's essentially the same, but the interaction term, the same 2 terms, but now we have this index J. So we have n atoms in the system. Okay. So and after introducing these bosonic operators, this interaction Hamiltonian can be written in this form. So this is where square root of n appears. Right. So this is just by going from the James Cummings to Tavis Cummings or Diki, we can see that. But in both cases, we are doing rotating wave approximation. So this comes from electron spin resonance or a nuclear magnetic resonance. You have a DC magnetic field around which the spins are precessing. And then you come in with an in-plane AC magnetic field, which can be decomposed into two circular polarizations. So here, so the spin and spin and photons are moving together. So yeah, co-rotating. But here it's So yeah, so basically within the rotating wave approximation, we ignore this. So that's what you do in the James-Cummings type Hamiltonian. But already in 1940, Bloch and Sigurd considered the case that where the light intensity is large, or the light matter coupling is stronger. In this case, you have to go beyond the rotating wave approximation. The so-called counter-rotating terms must be kept. What this means is that in addition to this and this, we have to include these rather counterintuitive terms. So that you destroy photon, and then you go down, and then you create a photon, but the matter also goes up, right? But yes, these are called counter-rotating terms. In addition, if you start from the minimal coupling Hamiltonian, you always end up with this A squared term. And then if you write down the A squared term using these operators, so this additional term appears. So all these are photon operators, but the coefficient depends on G. So this term appears only in the presence of light matter interaction. This becomes extremely important in the ultra-strong coupling regime. So on this project, we collaborated with a theorist in Osaka, Motoaki Bamba, who wrote down this Hamiltonian to explain our yes. Electron density. So yes. So that's here, within G. Only within G. Yes. So G is not G0. G, so square root is included. Any other questions? Yeah. So the essential physics is yeah, I already explained. So this is the matter Hamiltonian, cyclotron, Landau quantized electrons, the photon Hamiltonian, and the interaction Hamiltonian, including both the rotating and counter-rotating terms, and the A squared term. And yeah, so it looks more complicated, but because this is not a two-level atom. But the interesting thing is we can turn on and turn off different terms to see what each term is doing here. So here I plotted our experimental data. So the cyclotron resonance inactive was originally this side, but we flipped over to the positive side so that we can easily compare between experiment and theory. So here first, without counter-rotating terms, without A squared terms, so that nothing, so no agreement between the two. But first I include the A squared term. So this is with, this is without, with, without, with, without. So what you see is when you include the A squared term, all the three branches go up. So basically you're adding some sort of 0-point energy. So everything is going up. Okay. Now next I include the counter-rotating terms. So this is with, without, with, without. Note that only the cyclotron resonance inactive mode is affected. So nothing happens on the positive side. So this makes sense, right? So this proves that the Bloch-Sigurd shift we saw on the negative magnetic field side is purely due to the counter-rotating terms, not the A squared term. So this is, and if you include both all the terms, now we have agreement between the theory and experiment. Right. So the basic message from this first experiment is, so yeah, we're seeing polaritons, the hybridization of light and matter, and if the coupling is small, in the system, everything should be happening only on the positive magnetic field side. Nothing should be happening here. But as G over omega 0 increases gradually, then the influence of this extends over to the negative magnetic field side. So this is called the vacuum Bloch-Sigurd shift, and this is direct evidence for the breakdown of the rotating wave approximation. So that's the message of the first part, and also we see that the 2G is cooperatively increasing as a linear to the square root of n. So this square root of n. So we call this Diki Cooperativity, and Diki Cooperativity is the topic of the second topic. Okay, so let me explain that. Let me give you a little bit of background why we're interested in doing this. So in 1973, two theory groups published papers predicting the existence of a phase transition, now called the superradiant phase transition, or Diki superradiant phase transition. This happens when G becomes larger than omega 0. The basic idea is, as a function of G light matter coupling strength, let's say, so this is the original two levels, and the vacuum Rubby splitting occurs, and when the coupling becomes larger and larger, splitting becomes larger and larger, and eventually, when the lower Polariton branch's energy becomes lower than the energy of the original ground state, phase transformation is expected to go into this new phase called the superradiant phase. What do you call it? The order parameter is the mean photon number, which is 0 in the cavity. Again, we're not talking about external driving. Everything is happening inside the cavity, so the mean photon number is 0. But then this becomes finite when G becomes larger than omega 0. So they constructed a phase diagram as a function of temperature and the coupling strength. So the new phase is predicted in this shaded area. And note that this phase transition occurs even at 0 temperature as a function of G over omega 0. That's why more recent theoretical studies focused on this phase transition around here, studying this as a quantum phase transition. So the phase transition is not due to thermal fluctuations, it's due to quantum fluctuations. But this prediction, 1975 prediction, was immediately attacked by another group in 1975, saying, predicting a no-go theorem, reporting a no-go theorem for Diki phase transition. So the argument was basically, in the 1973 papers, they did not include the A² term. But these people said if you include the A² term, this phase transition is gone. That was their argument. But it turns out that it was not not a simple matter. So theorists kept arguing, discussing in the literature, 1978, 2004, 2007, 2014, 2014, and 2018, 2019, 2019, and 2019. There's an archive. This is Alan McDonald Polanyi. So basically, okay, I'm not a theorist, so but the point seems to be the gauge invariance is broken if you're not careful. So you have to be very, very careful to treat this. But also, yeah, Alan also predicts a no-go theorem. But the most interesting paper for us is this. 1978, Knight and co-workers considered a magnetic situation, because all the other papers start from standard light matter coupling at A dot P or E dot X or something. But here, so in a magnetic system, even the starting Hamiltonian is totally different. So there's a possibility that there's no term that corresponds to the A² term in the magnetic context. So that's why, so the Diki transition is probably possible. So that was the original motivation for us to study a magnetic system. So this particular system we're looking at is it's an antiferromagnet. So there are two subsystems. One is ions, and the other is erbium ions. They're both magnetic, but in the temperature range we studied, the ions are antiferromagnetically ordered, but the erbium ions are still paramagnetic, independent. Okay, and the ions produce magnons, coherent magnons, which we can excite easily in the using our time. Okay. And further, thank you. Interaction with the ions, exchange splitting further occurs. Okay. And then when we apply an external magnetic field, further Zeeman effect occurs. And all these low energy transitions occur in the terahertz frequency range, and this is an orthorhombic crystals. And depending on the direction of the DC magnetic field and the crystal axis and the terahertz polarization, we get very, very complicated spectra. But the most important transition I will talk about today is this transition A. This is the simplest picture of this is electron spin resonance. So electron paramagnetic resonance. So spin up and spin down. So this transition changes as a function of magnetic field. And so we have two subsystems. Erbium spins, they show the electron spin resonance, and then the magnon. And these two frequencies change as a function of magnetic field, and at a certain magnetic field they meet. When they meet, they show anti-crossing, and this anti-crossing turns out to be ultra strong. And so the analogy is this: so we have a collection of two-level atoms, right? So the spin up and spin down, and we have a bosonic field, which is, so instead of a photonic field, we have a magnonic field. And when they, so Motoaki again, constructed the Hamiltonian, but then after some manipulation, so he ended up with this. So this is very basically the same as light matter, but no A squared term. Right. So we see this anti-crossing and this crossing. So this splitting. Yeah. Okay. So here we change the number of spins by changing this composition X. So yttrium does not have any spins. So we by replacing erbium with ytterbium, we are diluting the spin density. Okay, so by doing this, we were able to show that the splitting is proportional to the square root of the spin density. So this is a rather unique magnetic manifestation of Diki cooperativity. So that's the main message of the second part. So let me move on to the last part: exciton polaritons in aligned carbon nanotubes. So let me start with with a brief introduction to carbon nanotubes. So many of you are familiar with graphene, probably. So basically, the carbon nanotube it is a rolled up version of graphene. So carbon is sp2 bonded, and the typical diameter is only 1 nanometer. but the length can be macroscopic. Even it can be even millimeters. So the aspect ratio is enormous, and so they possess unique one-dimensional quantum properties, and they have been studied for the past 2 decades, especially on the single tube levels. So the challenge is when you make an assembly of carbon nanotubes. Typically, they are randomly oriented, and also that all the properties depend on the diameter. So if your ensemble of carbon nanotubes contains metallic and semiconducting nanotubes with different diameters, you end up with a very disordered system. So we want to keep the one-dimensionality and the purity of the electronic structure. So very recently, we reported a new method for making wafer scale films in which the carbon nanotubes are extremely well aligned and highly packed. And at least locally speaking, we have a crystal-like structure. Okay? So these nanotubes spontaneously aligned and globally aligned and highly packed. And these films are very robust, and they are compatible with standard microfabrication technology. And these aligned nanotube films are extremely anisotropic in many properties. For example, if you look at their optical response, so this is T is transmittance, so this is basically attenuation. Attenuation versus photon energy for 3 orders of magnitude, from 1 millieV, which is very far infrared, 1 EV is near infrared, and when the polarization is perpendicular to the carbon nanotube axis, essentially there's no attenuation. So the light doesn't see the film. But if the polarization is parallel to the nanotube axis, there's huge interaction, intraband and interband interactions. And if you look at this, if you carefully determine the real and imaginary part of the dielectric constant for the 2 directions, this is what we get. So the solid lines are the real part, and the dashed lines are the imaginary part of the dielectric constant for the perpendicular and parallel directions. So let's just focus on the real part. So if you look at the real part, perpendicular, basically nothing. This is a weak dielectric, right? So it's no features. Always the dielectric constant is positive and no features. But if you look at the parallel part of the dielectric constant, there's a sign change. In the interband absorption regime, it's positive. But as we go into the mid-infrared and terahertz range, due to free carriers, due to the plasmonic or Drude-like response, it's metallic. So basically, in this regime, it's dielectric in one direction and metallic in the parallel direction. And this kind of system is called hyperbolic, because I don't have that today, but basically the equi-frequency contour is open. It's hyperbolic, hyperbola. Okay. Yes. But today's topic is we again put this in a cavity. So in this case, it's a simple Fabry-Perot cavity, and we start with a glass transparent substrate, and we deposit a bottom mirror, and then we deposit a PMMA spacer. So this is just to adjust the thickness, and then at the center we have a thin film of aligned carbon nanotubes, followed by another spacer and the top mirror. And basically the cavity mode has a maximum which coincides with the location of the carbon nanotube film. So traditionally, let me explain the microcavity exciton polaritons. So you have 2 mirrors, and you have a 2-dimensional system, typically gallium arsenide quantum well, which contains excitons, and there's a photonic mode which strongly interact with the excitons. So I want to emphasize that this is a 2-dimensional system. So the So if this is the K, so this direction is quantized, but still excitons and photons have the in-plane momentum included. So here, dispersions for the polaritons, energy versus wave number. So this wave number is either kx or ky in the plane. So so this is the photon dispersion. So this is not linear because of the cavity confinement in the z direction. Okay, so this is the in-plane moment. This is photon dispersion, and the compared to the photons, exciton mass is huge. So the exciton dispersion is flat, and they meet. Oops, sorry. And so this is the upper polariton, this is the lower polariton, and the difference between the two is the Rubby splitting. And if you look at this from an angle, this is isotropic. So kx and ky, they're equivalent. So there's a gap between the two throughout, right? In our case, so this is our case. Again, the y-axis is the energy. So this is energy, and then okay, z is energy, x and y, and as you can see, so the gap depends on the direction. So here we have ultra strong coupling, but here no coupling, weak coupling, no absence of polaritonic gap. Okay, so the two modes coalesce, and then it stays. So there are two arcs in the K momentum space where the upper polariton and the lower polariton touch each other. Okay, why is this possible? Yes, that's because of this. So essentially, so we have two angles in our experiment. So phi and theta. So by changing the theta, the incident angle, we can map out, we can couple with finite momentum excitons or polaritons. So that's how we change. That's how we map out this dispersion, theta. But in addition, we have this knob, polarization angle between the incident polarization and the alignment direction. And if that angle is 90 degrees, the splitting is gone. But when it's parallel, we have this splitting. This is due to the polarization selection rules in carbon nanotubes. And the splitting is huge. So the exciton energy is, in this case, 1.2 eV, and the splitting is 300 millieV. So we are in the ultra strong coupling regime. And what typically, so in typical 3-5 semiconductors like gallium arsenide, this ratio would be 10 to the minus 3, sometimes 10 to the minus 4. So here we're talking about 0.1. And we confirmed that by changing the thickness from 8 to 64 nanometers, what we're doing, we're changing the total number of excitons, total number of nanotubes, and we see this Diki cooperativity again. So let me summarize. So we're doing resonant optics and exploring new regimes of light-matter interaction where the Rubby energy is comparable to or even larger than the photon energy used. And we are taking advantage of the fact that condensed matter systems have so many electrons. So many body effects and cooperative enhancement occurs thanks to these electrons. So, but also beyond Diki, so everything is understood in quantum optics. But this is just one aspect of many body interaction. There are many other types of electron-electron interactions in real solids. So that will make this system or field very interesting. So at the boundary between quantum optics and condensed matter physics. So we also have this unique tunability. So let me thank my co-workers. So all the experiments were done by my group. Xinwei Li and Qi Zhang did most of the measurements, together with some collaborators here in Yokohama and Germany. So the samples came from 3 different places: Mike Mumfra, Purdue University, and John Reno, Sandia National Labs. And the magnetic samples came from Shanghai University. And we are collaborating with 2 theorists. Thank you.
for this magnetic system spins interaction via magnet. Did you observe this or are going to observe this?
We do observe a phase transition. All the data I showed you today and published were done at rather high temperature. So the lowest temperature in that data set was 10 Kelvin. But actually below 10 Kelvin, there's a phase transition. Very interesting. And we are right now trying to explain this phase transition as one type of Diki phase transition. But it's not a simple Diki. We need to add some extra terms to the Diki Hamiltonian to explain the data. But there is a phase transition in this system. Low temperature.
You have to explain why you don't have a squared term for it.
Because the A squared term comes from the...
For the magnons, don't have. You have to
Right.
explain this.
So this... Right, so we don't have this. So this kind of light matter. So A represents the light field, but this kind of starting point doesn't apply to the magnetic context. So
You should explain why.
Why?
Why magnons decide that they differ. This is important. To understand why magnons are different. Of course, there's a different
Right.
nature. It should be different, but why exactly? But I don't ask this to do this now.
Right. But my understanding is that there's no classical counterpart. So everything here is due to exchange interactions. So this... Right.
And you speak all the time about spin. We should know that.
No, this is the usual dipole, electric dipole interaction, right? But our system is different. Yeah.
Yes.
So when the quantum phase transition occurs, you show that the number of photons inside the cavity is non-zero. When the number of photons inside the cavity is non-zero, how many come out of the cavity?
So they don't come out unless you perturb the system. So the ground state. Oh,
They can be grounded in the system as non-zero photons, so they don't come out of the cavity, right?
right,
They don't come out. Why they don't come out?
because that's the ground state. We can consider the following experiment. So you start with this new phase, and then all of a sudden we change the Q of the cavity. For example, you do a quantum quench experiment. Then this original ground state becomes an excited state of the new Hamiltonian. So in that case, the original ground state will relax to the new ground state. During that process, some radiation can come out. So these are called Casimir photons, and because these photons come from vacuum, right?
One more question.
Yes.
Your system with this Diki phase transition is similar to the experiments when they have a scattering of fields with
What is it?
pumpkin.
Permanent pump.
Scattering occurs in the cavity, and they also have a system without A square. And they observe this kind of effect on this system.
Yes. Okay. So you're talking about
A lot of experiments in
Right.
last decade about this. You have completely different magnets.
Yeah. So okay. Thank you.
Yes. So why use the? I mean, how they to describe this super radiance transition?
Yes.
So why don't use the electric field itself?
Electric field itself.
This transition instead of using the photon number in the cavity. So I think
I see. Yeah.
the electric field is kind of proper for the
Actually,
simultaneous breaking.
I think you're right. Yeah. So Motoaki Bamba told me the same thing. Yes. Yeah, the field should be yes, yes.
Yeah,
Right.
if the number is, if there's non-zero number is heavy, but that doesn't mean there's the field itself is non-zero.
Right. Yeah, I think you're right. Yeah.
All right. Yeah.
Um, loss. So yeah, absorption occurs, but so absorption is due to the resonant light matter interaction. That's the main thing we are studying, right? So I don't quite understand the question. I don't. Are you asking what determines the line width, or no?
I mean, you have to couple exotones in carbon nanotubes with light, right? So that's what it does. Of course, this is inevitably described as the imaginary part of flexibility, but that's what you need for coupling. The point of strong coupling is that it's not like loss. I mean, that it get absorbed, that's it, or photons get emitted, that's it. It's always, the photons come back many, many times, and there is constant exchange of energy between photons and exotons. So that's the nature of the strong coupling. So you need the absorptions in order to couple.
So emission can be used as a probe. So here we're using absorption as a probe. So we can do absorption spectroscopy or photoluminescence spectroscopy, either way.